For section 4.4, we're going to talk about recursive definitions. We say a sequence is defined recursively provided it has two parts. The first part says some finite set of values, usually the first one or the first two, which are specified. And then the remaining values of the sequence are defined in terms of the previous values in the sequence. Such a formula is called a recurrence formula or a recurrence relation. The requirement they have here as B gives the basis or starting point for our recurrence. The remainder of the sequence is determined by the relation R applied repeatedly, aka recurrently, over and over again. So we'll look at some examples of recursive definitions here, starting with this one that defines the sequence FACT, fact, recursively. And so the first part says that fact of 0 is equal to 1. That's the basis or starting point for the definition. And then it says that fact of n plus 1 equals n plus 1 times fact of n. What this means is if I try to calculate fact of 1, I take 1 times fact of 0, the prior number in the sequence. And so that would be 1 times 1, or 1. And then fact 2, we would take 2 and times it by fact of the last number, 1. So again, recursively means we're taking the previous value and applying it to the next. And so that would look like 2 times 1, or 2. And then fact 3 would equal to 3 times fact 2. And that would be 3 times 2, or 6. And we could keep going on this way. It'd be 4 times the value from the last step, so fact 3. So that would be 4 times 6, or 24. And so this would be how we visualize the values of this recursive definition here. And in general, actually, this thing, fact of n, is going to be the same as in factorial. So this is a recursive definition for factorial. The next one says create a recursive definition for the sequence sum of n equals the summation I equals 1 to n of 1 over I factorial. Okay, here's how we can do this. The first thing is to define the basis of our recursion. So the very first one, sum of 0, would be equal to 1. Because if I plug in 0 here, it would look something like 1 over 0 factorial, 1 over 1, which is 1. So that's the first value. Now to get to the next value in this sequence recursively, or the sum of n plus 1, what I'm going to do is take the sum of the first n and then add to that 1 over n plus 1 factorial. Since that's how our summation works up above, it goes 1 over 0 factorial plus 1 over 1 factorial plus ... 1 over n factorial. So if I want to go all the way up to here, that's taking the first n and adding them together. And then if I want to add another one to that, I could go plus 1 over n plus 1 factorial to that, to everything that's been calculated before. So if we go through here and calculate a few values, so for instance the sum of 0 is equal to 1, and then the next one, sum of 1, would go sum of 0 plus 1 over 0 plus 1 factorial, which would be 1 plus 1 over 1 factorial, which is equal to 2. And then the sum of 2 would equal to the sum of 1 plus 1 over 1 plus 1 factorial. That would equal to 2 plus 1 over 2 factorial. That would equal to 5 over 2. And then the sum of 3 would be the sum of 2 plus 1 over 3 factorial, which equal to 5 over 2 plus 1 over 3 factorial. That would equal to 8 over 3. And then it just kind of continues on from here. Okay, now on this next one it says define the sequence of t by t of 1 is equal to 1, and then t of n is equal to 2 times t of the floor of n over 2. We're going to start by finding t of 73, but by only using t of 36, 18, 9, 4, 2, and 1. So here's how I'm going to do this here. T of 73 is by definition up above same thing as 2 times t of the floor of 73 over 2. Okay, now that's the same thing as 36. So 2 times t of 36. Now I can expand that because t of 36 is 2 times t of the floor of 36 divided by 2, or 18. And so that can continue to be expanded out because t of 18 is the same thing as t of 9. Or 2 times t of 9, I should say. So t of 18 turns into this. And so we can keep going this direction here. We take t of 9, okay, and write it as 2 times the floor of 9 divided by 2, which is 4. Okay, we can still keep going here. We have all these 2's still multiplied together, but t of 4 is still something as well. So t of 4 is 2 times t of 2. And then lastly, let's just write this as 2 times 2 times 2 times 2 times 2 times, and then finally down here t of 2 turns into 2 times t of 1. So now we've fully gone back down to the very starting basis of the recursion, t of 1. So this is going to be equal to 2 to the 6th times 1, or just 2 to the 6th. So this is how we can kind of go through the recursion backwards, starting from t of 36, 2 times t of 18, 2 times t of 9, 2 times t of 4, 2 times t of 2, and then it all multiplies together from there. Now to write this what they call iteratively, that means write it in a way that's not recursive. So we found out that t of 73 is equal to 2 to the 6th. It turns out that what t of n is the largest integer, 2 to the k, with 2 to the k less than or equal to n. We can see that because t of 73 was 2 to the 6th, and that's equal to 64, which is less than 73. Less than 2 to the 7, which is 128. So it's figuring out, if we're given a 73, figuring out the power of 2, that you can raise that to get that number between. So it's between 2 to the 6 and 2 to the 7 here. So that's a way of defining this iteratively, where we can just go straight to the number rather than having to go recursively. Now in this example here, it says to describe the sequence and write recursively its set of values. Okay, so let's start out with some of the values we have here. it looks like it goes 0, 0, and then it jumps to 1, 1, 2, 2, 3, 3, and it just keeps going back and forth. So sequence of 0, we'll call it here, is equal to 0. Sequence of 1, the next one over, is equal still to 0. Sequence of 2 is equal to 1, and it goes from there. So to set up the basis of this sequence, what I'll do is set the sequence of 0 equal to the sequence of 1. So the first two entries in the sequence will be just equal to 0, just like we have up above. And now we can set up a formula so that these will start repeating, but only 2 at a time. So our recursive part of the definition here will say sequence of n will be 1 plus the sequence of n minus 2 for n greater than or equal to 2. Now we will need to double check and make sure this works. It's going to take 1 and add it to the entry that's 2 steps behind. So for instance, if we start from sequence of 2, we already have the first 2 defined up above as 0, then that would be 1 plus the sequence of 2 minus 2, or 0 in other words. So that would be 1 plus 0, which is 1. And then the sequence of 3 would be 1 plus sequence of 1. So that's still 1 plus 0, which is 1. So that matches what will happen in our sequence up above. And if we keep going to the next, it'll take 1 plus 1 to give us 2. And it'll do it again for another 2 until it goes on and moves up to 3. Now for this one, it says we're going to find S of 73 recursively. Okay, and our recursive definition is given up above. So kind of similar to another example we did here. If we look at our recursive definition up above, we can say that S of 73 is going to start out as S of the floor of 73 divided by 2 plus S of the floor of 73 divided by 5. Now what that's going to equal to is S of 36 plus S of 14. Okie doke. Now S of 36 and S of 14, we're going to break those down by the recursive formula as well. Okay, so that's going to first off be S of 18 plus S of 7 for the first one here, plus, and if we break down S of 14 with the formula, it would be S of 7 plus S of 2. Okay, but now each of these need to be broken down with the recursive definition as well. So what we're going to have here is S of 9 plus S of 3 plus S of 3 plus S of 1. Okay, that goes with this one here. Okay, and then we'll have plus S of 3 plus S of 1 plus S of 1 plus S of 0. All right, that's going to be for this part and this part here. Okay, now we have to keep breaking this down even further, but we can simplify it a little bit at this point because we kind of have some like terms that can be joined together. If we join together like terms here, we'll have S of 9 plus 3, S of 3 plus 3, S of 1 plus S of 0. A little bit more manageable this way. But we still need to break down the S of 9, the S of 3. Our recursive definition gives us the basis, which gives us those two, S of 0 and S of 1. So we don't have to break those down. For S of 9, that would look like S of 4 plus S of 1. Okay, plus 3 times s of 1 plus s of 0 plus 3 s of 1 plus s of 0. So doing some more cleanup here, this would be s of 4. Then now we'll have 7 times s of 1. So the next thing we have to do is plug s of 4 into the recursive formula. That'll give us s of 2 plus s of 0. And we'll still have the plus s of 1 and plus 4 s of 0. Okay, and so we'll combine together like terms. We have s of 2 plus, we'll have 7 s of 1 plus 5 s of 0. Now we still have to go one more time with s of 2 into the recursive formula. That would equal to s of 1 plus s of 0 plus 7s of 1 plus 5s of 0. So altogether, when we combine like terms, we'll have 8 s of 1 plus 6 s of 0. Altogether, that'd be equal to 8 times 1, since we know s of 1 is equal to 1, and s of 0 is equal to 0. So this would all be equal to 8. Now for example 5, it says consider the sequence 1, 3, 9, 27, 81, and so forth. Give a formula for the nth term, sequence of n, where sequence 0 equals 1, and give a recursive definition. So the first question we should ask ourselves is, how are these numbers being constructed? Well, they look like they're in powers of 3. So the first one would be 3 to the 0, 3 to the 1, 3 squared, 3 cubed, 3 to the 4th, and so on. So each one is generated by multiplying the last one by 3 is another way of thinking about it. So we can define this recursively with the basis of this SEQ sequence of 0 is equal to 1. And then the recursive step here can be defined by taking sequence of n plus 1 as equal to 3 times sequence of n for n greater than or equal to 1. And that's this, again, the same thing as just saying 3 times the previous number calculated. So we'd start with 1, then we get 3, and then 3 times 3, 9. 9 times 3, 27, 27 by 3, 81, and so forth. For example 6, what we're going to do is define a recursive sequence with b sub 0 equals b sub 1 equals 1, and b sub n equals 2 times b sub n minus 1 plus b sub n minus 2 for n greater than 2. We're going to calculate b sub 5 and then look into why all the terms are odd. So b of 5, by definition, would be equal to 2 b of b sub 4 plus b sub 3. Now b sub 4 can be calculated as 2b sub 3 plus b sub 2. b sub 3 can be calculated as 2b sub 2 plus b sub 1. Okay, and cleaning this up a little bit, this is equal to 4b sub 3 plus 4b sub 2 plus b sub 1. But we need to break down b sub 3 and b sub 2 as well. So here we'll have 4 times 2b sub 2 plus b sub 1 plus 4 times 2b sub 1 plus b sub 0, all plus b sub 1. Clean this up a little bit, that's 8b sub 2 plus 13b sub 1 plus 4b sub 0. Okay, we need to break down b sub 2 still further, so that's going to give us 8b sub 1 plus b sub 0 plus 13b sub 1 plus 4b sub 0. So what we're going to get here when combining everything together is 29b sub 1 plus 12b sub 0. We know b sub 1 is equal to 1, and b sub 0 is equal to 1. So when we add this all together, we'll get 41. Now, to discuss why the terms turn into odd numbers, let's think about how it goes here. Our first two numbers, b sub 0 and b sub 1, are both odd as 1. And again, our sequence is 2, b sub n minus 1 plus b sub n minus 2. And so if we were to plug in numbers here to find, say, b sub 2, then that would be 2 times 1 plus 1. And that's equal to 3. And so every time we're calculating this, like b sub 3 would be 2 times 3 plus 1. So that would be 7. b sub 4 would be 2 times 7 plus 3. So as we can see, we're still adding numbers here. Odd number, well, first number is an even number, but since it's multiplied by 2, adding an even number and an odd number together, that's always going to result in an odd number. And so we see that will happen down the line here each and every time, since the first part's even, it's multiplied by 2, but we're always bringing forward an odd number from our previous numbers in the sequence.